In this video, we're going to discuss the mean value theorem. Now, the mean value theorem doesn't get used that often in and of itself, except to give you a ticket on a toll road where it gets used a lot, but it is one of the foundational theorems of all of calculus. It's used in some of the most important theorems down the road, including the fundamental theorem of calculus. And some of the corollaries or resulting theorems or ideas from the mean value theorem enable us to learn more things about the shapes of graphs of different functions. We're going to start with an application of the mean value theorem, a special case called Rolle's theorem. Let's go ahead and start with Rolle's theorem. Informally, Rolle's theorem states that if the y values, the outputs of a differentiable function, a function with a derivative, are equal at the endpoints of an interval, that is, the two y values at either end of the interval are equal to each other, then there must be at least one point C interior to the interval on the inside of the interval where the slope of the tangent line at that point is 0. In other words, if the y values are equal at the ends of the interval, and it is a differentiable function, which means it has to be continuous and it has to have a derivative. So that means because it's continuous, we can have no holes, no displaced points, no tangent lines that are vertical, and no jumps. And because it's differentiable, that means that we can't have corners, cusps, or points of vertical tangency. So if we have this differentiable function and the y values at the endpoints of the interval are equal to each other, no matter what they are, then there has to be at least one place in the interval between A and B where there's a C value and the slope of the tangent line at that point is 0. Basically, if the function gets back down to here and you can draw it in a connected curve that has no corners, cusps, or vertical tangent points, because it comes back to where it started, there has to be a place where it turns around. If it goes increasing and then decreasing, we have to have a relative maximum. If it goes decreasing to increasing, we have to have a relative minimum. Now, it says at least one. That doesn't mean we can't have more than one. On this last graph on the far right, you'll see that the endpoints of the interval do have the same y value, the same output. And there are, in fact, two C values between the points A and B, where the slope of the tangent line, the derivative at C1 and at C2 is 0. This is Rolle's theorem. Now we want to state Rolle's theorem more rigorously. Let f be a continuous function, so we have no holes, no jumps, no displaced points, no vertical asymptotes, over the closed interval from A to B. So that means that it's continuous from the right at A and continuous from the left at B. That means the function exists, the two-sided limit exists, and they're equal to each other. Also, let the function f be differentiable over the open interval from A to B. So at every point on the interior, we have a limit of the difference quotient that comes out to be some function, such that f of A is equal to f of B. The function value, the y value, at the endpoints of the closed interval are the same y value. Then there exists at least one C in the open interval from A to B, such that f prime of C equals 0. Now, note that if these conditions are not met, then Rolle's theorem will not apply. And what are the conditions of Rolle's theorem? There are 3, and I've numbered them for you. It has to be a continuous function over the closed interval from A to B. It has to be differentiable over the open interval from A to B. And third condition, f of A equals f of B. If any one of these fails to be true, then Rolle's theorem may not apply. It might not. Chances are it won't. Now, it's not guaranteed, and that's the problem. Let's look at an example of one that does not meet all the conditions and the conclusion of Rolle's theorem does not apply. We're looking now at the graph of the absolute value of x minus 1. So it looks like a V and it's been shifted down 1. So we have this graph and we're looking at the graph over the interval from -1 to 1. So remember the three conditions for Rolle's theorem. It's continuous on the closed interval. Does the function value exist? Does the two-sided limit exist? Are they equal? Yes, between -1 and 1, all of those things are true. You can also do the hand waving definition. You can draw it without picking up your pen between -1 and 1. It is continuous. Is it differentiable between -1 and 1? Here's where we have a problem. We have one point, x equals 0, where we have a sharp corner. Anywhere we have a corner or a cusp or a point of vertical tangency, the first derivative does not exist. So we have a point here on the interior of the interval between open -1 and open 1 where the first derivative doesn't exist. Because it's not true over the entire open interval, it's just not true. It's sort of a one and done. And that means that that second condition of Rolle's theorem is not met. What about the third condition? F of A equals F of B. Well, we can see that the function value at -1 is 0, and the function value at 1 is also 0. So condition 3 is met. So conditions 1 and 3 are met, but condition 2 is not. And note that on this particular graph, there is no point C between -1 and 1 where the slope of the tangent line is 0. That's because we have a corner down here at this point. And at that point, the first derivative does not exist. It's not any value at all. It's not defined. Now we want to take a look at example 1. In example 1, we want to verify that the function f 2x squared minus 8x plus 6 defined over the closed interval from 1 to 3 satisfies the three conditions of Rolle's theorem. And then we want to find the points C that are guaranteed by Rolle's theorem. Now, Rolle's theorem is what we call an existence theorem. It tells you that the points C exist, but it doesn't tell you how to find them. So we're going to see if we can figure out how to find those points C. First, we want to prove that it satisfies the three conditions of Rolle's theorem. So our function, again, writing it down here, is 2x squared minus 8x plus 6. Condition 1 is it has to be continuous over the closed interval. So continuous on the closed interval from 1 to 3. And the answer is yes, it is. Why? Because it's a polynomial. Polynomials are continuous on the entire real number line. So we know it is definitely continuous between closed 1 to closed 3. Part 2, is it differentiable on the open interval? So for that, we have to consider, again, the function. Does it have a derivative at each point on the interior of the interval between open 1 and open 3? And again, the answer is yes, for the same reason. It's a polynomial. Polynomials are our favorite class of functions for a reason. They're continuous everywhere, and they're differentiable everywhere, and they're defined everywhere. So they have very nice behavior. So yes, it is differentiable on the entire real number line, so it's certainly differentiable on 1 to 3. The last condition is that the function value on the endpoints is the same, that they're equal to each other. So for condition 3, we need to find what f of 1 is, and then we'll need to find what f of 3 is and establish that they're equal. F of 1 would be 2 times 1 squared minus 8 times 1 plus 6. That's 2 minus 8 plus 6, which basically gives us 0. Plugging in the value of 3, we get 2 times 3 squared minus 8 times 3 plus 6. This gives us 2 times 9, which is 18, minus 24 plus 6. Again, we end up with 0. So we find that the function value, the y value at the two endpoints are equal. So now we have that f of 1 is equal to f of 3. This meets condition 3. Now we want to find the value c, where the slope of the tangent line between 1 and 3 is equal to 0. In order to do that, we need to find the derivative. So we're going to look at our function, f of x equals 2x squared minus 8x plus 6, and we're going to find the first derivative. Finding the first derivative gives us the following. F prime of x is equal to 4x minus 8. At what value would the first derivative be 0? To find where it's 0, we'll set 4x minus 8 equal to 0 and we'll solve. This gives me 4x equals 8, or x equals 8 over 4, which is equal to 2. In other words, is 2 inside my interval between 1 and 3 open on both ends? And the answer is yes, it definitely is. So in this case, we've seen that there is a value for which the derivative, the slope of the tangent line, is equal to 0 when the endpoints, the outputs or y values, are the same at the endpoints. Let's graph this one onto a graph and see what it looks like. We have 2x squared minus 8x plus 6. 2x squared minus 8x plus 6. Now we only are interested in the interval between 1 and 3, so we can use curly brackets and Desmos to do 1 less than equal to x less than equal to 3, and close with more curly brackets. And now if we look at this particular graph and blow it up so that it's a little bit larger, we can see that at the two endpoints, the y value right here is 1, 0, and the y value over here is also 0. So we have 1, 0 and 3, 0. There has to be a point in between where the slope of the tangent line is 0 by Rolle's theorem, because it meets our three conditions. And we see that that point is at x equal 2. When you're at x equal 2, which is right down here, the tangent line is horizontal, which means the slope of the tangent line is 0. Now we want to move on and we want to discuss the mean value theorem, the most valuable theorem, as some professors like to refer to it. It is the main topic of this section. So again, Rolle's theorem is a special case of the mean value theorem. So in a sense, Rolle's theorem is a part of the mean value theorem, but the mean value theorem doesn't have the same number of conditions. It only has 2. In fact, what the mean value theorem does is it generalizes Rolle's theorem so that the outputs, the y values at the endpoints, do not necessarily have to have the same value. That's a pretty big restriction, that the y values at the endpoints be the same. So we take that condition out and we find instead that the mean value theorem will tell us that whatever the slope of the line connecting the endpoints, the secant line, whatever that is, as long as the function is continuous on the closed and differentiable on the open, then there has to be a C between A and B where the slope of the tangent line is the same as the slope of the secant line. Let's now take a look at a graph so that we can see what this means in terms of the graph. Looking at the graph, note that the endpoints no longer have necessarily the same y value. They could, that would be Rolle's theorem, but they no longer are required to. They can have different y values. If you connect the two endpoints with a line, we would call this the secant line. So the secant line is this line right here, which I'm going to overcolor in a dashed blue line. So this is our secant line connecting the two endpoints of the interval. As long as the function is continuous over the closed, so that we have no holes, no jumps, no displaced points, no vertical tangent lines, or vertical asymptotes rather, and differentiable over the open, meaning no corners, no cusps, and no points of vertical tangency as it goes up between A and B, then there has to be a point C that's between A and B, open, where the derivative at C has the same slope, has the same value as the slope of the secant line. In other words, they're tilted the same. Whatever the slope on the tangent line is, it's the same as the slope on the secant line. That's all the mean value theorem tells us. So here is the statement of the mean value theorem. Let the function be, number one, continuous over the closed interval from A to B, and two, differentiable over the open interval from A to B. Then there exists at least one point, maybe more, but at least one, between open A and open B, such that the slope of the tangent line, f prime of C, is equal to the slope of the secant line. And this, of course, is just the difference quotient that you're used to seeing from college algebra. It's also y1 minus y2 over x1 minus x2. It's slope, but it's the slope of the secant line. So what we have here is slope of the secant line on the right side and slope of the tangent line on the left side. Now let's talk briefly about the proof. The proof uses Rolle's theorem, right? So it follows Rolle's theorem, and what it does is it creates a new function. So we have some function. We assume that it is continuous over the closed, differentiable on the open. We want to be able to apply Rolle's theorem, but the problem is our endpoints probably don't have the same y value, the same output. So instead, we create a new function, and we're going to look at the new function and define it in such a way that it satisfies Rolle's theorem. Now we need to connect the endpoints, which is A f of A and B f of B, together to make the secant line. And the slope of that line is given by y1 minus y2 over x1 minus x2. This is the slope of the secant line. And of course, the line goes through the points A f of A and B f of B. We choose one of the points, typically the first one, A f of A, and we write the equation of that line now as follows. This is the point slope form of a line, y minus y1 equals slope of the secant line, x minus x1. We use f of A for y1, and we use A for x of 1. So we're using the point A f of A. Then we replace the slope of the secant line with the difference quotient, or y1 minus y2 equals x1 minus x2. Finally, we solve for y by moving the f of A to the other side, which makes it positive. And we get this expression here on the far right. Now we're going to define this new function on which we can apply Rolle's theorem. So what we're going to do is we're going to create a function, which we'll call g, to represent the difference in the vertical heights between the point x f of x and the point on the line, so the point on the secant line. So let's take a look now at what that might look like. So when we're looking at our graph, we're looking at defining this vertical distance between the secant line itself, which we just found the equation of that line, and the curve, which is the f of x. Whatever this vertical distance is, that's going to be the y value of our g function, whatever that vertical distance is. Whenever f of x touches or crosses the secant line, there's no vertical height. So the y value on g at those points would be 0. We can define g to be the function value f of x minus the y value on the secant line at any particular point between a and b. Now, we just got the equation of the line y equals, and that's what you see substituted here in the square brackets. This is slope of the secant line, f of b minus f of a over b minus a, times x minus x1, x minus a, plus y1, f of a. And we're subtracting that from the function value. That should give us the difference in the height between these two functions. So our g then is the height or the difference in the y values of those two functions. When we graph the g function, it's graphed down here in blue. Notice that at the points where the secant line touches the function, the y value is 0. And in between, this height here corresponds to that height there, and this height here corresponds to that height there. Now we have a function on which we can apply Rolle's theorem. Because the original function was continuous on the closed, g of x, which is the original function minus the equation of a line, also has to be continuous on the closed interval. Because the original function was differentiable on the open interval, then g of x, which is the original function minus the tangent or secant line, also has to be differentiable on the open interval. So we've met those two conditions. What about condition 3, that the endpoints have to have the same value? Well, because the endpoints of the function and the interval touch both the function and the secant line, then on g of x, the difference in y values of those two functions is 0. So these two have the same y value, which is 0. Now we can apply Rolle's theorem to it. When we're applying Rolle's theorem says there must be a point C between open A and open B where the derivative is equal to 0. Remember, that was Rolle's theorem. Mean value theorem, the slope of the tangent line equals the slope of the secant line. That's what we're trying to prove. So I need to take the derivative of g of x. G of x is defined to be the function minus y on the secant line. And the y expression is everything that you see here in the square brackets, just like it was above. So we have f of x minus all of this, which represents the secant line equation. Now, we're taking the derivative with respect to x. So if we were to multiply out some of what we have here, remember we would have to have that slope of the secant line times x and the slope of the secant line times a plus f of a. And all of this would be subtracted from f of x. So in other words, if I use m secant to replace f of b minus f of a over b minus a, this right here becomes f of x minus m secant times x minus m secant times a negative a, which would make it a positive m secant a plus f of a. All right. So now we have the function itself minus the slope of the secant line times the variable x plus the slope of the secant line times the constant a plus f of a, which is also a constant. Remember, a is the left endpoint of the interval. It's known, so is f of a. When we take the derivative of this, the last two terms will zero out. The derivative of a constant is 0, so the last two terms disappear. That leaves us with f prime of x and the coefficient of the second term, which is the slope of the secant line. And the slope of the secant line is represented by the difference quotient, f of b minus f of a over b minus a. When you're looking at this then, This says that g prime of x should be equal to 0. Remember, Rolle's theorem says there's a c, and the derivative at that point is equal to 0. So this part right here is equal to 0. If we move the slope of the secant line to the other side of the equation, then what we're basically saying is that this f prime at c minus the slope of the secant line has to equal 0, which implies, of course, that f prime of c is equal to the slope of the secant line. This is what we were trying to prove. F prime of c, this is the slope of the tangent line on the left. The difference quotient on the right is the slope of the secant line. So we've proved that the slope of the tangent line is equal to the slope of the secant line. This ends the proof, and we denote that with QED, quo erat demonstratum, which is Latin for enough has been demonstrated, or in grad school, quite enough, damn it. All right. Now we want to talk about a real world application for the mean value theorem, which has to do with velocity. Now, I said we don't actually use the mean value theorem on a daily basis very often, except on toll roads, where it gets used all the time. Why? Well, here's the idea. Your position at one toll booth and your position at the next toll booth tells them exactly what the distance is that you've traveled. They have a measurement of the time that you paid at the first toll booth and the time you paid at the second toll booth. And because they have the values at the two endpoints, they can find your average velocity. They take the distance and they divide by the time between when you checked in at the first toll booth and when you checked in at the second. Now, here's the tricky part. The position function is a continuous function over any amount of time. So certainly over closed 0 to however long it took you to get from point A to point B. It's also a differentiable function. So that means that we can apply the mean value theorem, which means that if your average velocity was 78 and the speed limit was 70, then the police officers know without a doubt and without being there and no radar gun that at least one time you were driving 78 miles per hour, and you get a ticket in the mail. They don't even have to be there. They just take the time from one toll booth to the next, the distance from one toll booth to the next. They compute the average velocity, and by the mean value theorem, they can assert that at least once you were traveling that average speed. Slope of the tangent line equals slope of the secant line. Instantaneous velocity at least once equals the average velocity. Let's now take a look at some examples. We'll start with example 2, which is a ball. We have a ball which is being dropped from a height of 200 feet. Its position at time t is given by the equation S of t equals negative 16t squared plus 200. Find the time t when the instantaneous velocity, slope of the tangent line, of the ball equals its average velocity, slope of the secant line. Now, where does this equation come from? First thing to note is the negative 16 is actually coming from the effect due to gravity. The effect due to gravity, if we call down the negative direction, it's 32 feet per second per second. And we're taking half of the acceleration for reasons you'll discover if you have to take a physics class. Now, the initial velocity when the ball is dropped, so basically you probably have a child who opens a window, hopefully they can't get out of, holds the ball out over this sidewalk 200 feet below and lets go. The initial velocity is 0, so we don't have a middle term. But the initial height at time equals 0 is 200 feet up in the air. So that gives us negative 16t squared plus 200. Now, what happens to the ball? The ball starts off at 0 velocity because it's being held still. And then it falls faster and faster and faster. And if we ignore the friction due to wind and air, then it will fall faster and faster until it reaches the ground. Now, because it's a ball, it's going to bounce. But we're going to ignore the bouncing, and we're just going to look at the part where it starts at the top until it hits the sidewalk for the first time. So one of the things we need to find is that time interval there from t equals 0, our left endpoint, which would be here, to our time when it hits the ground. So we need to find the instant where it hits the ground. To find the instant where it hits the ground, what we need to take is the function and set s of t equal to 0. The ground, the sidewalk, represents a distance of 0. So we want to take negative 16t squared plus 200 and set it equal to 0. Now, if we move the negative 16t squared to the other side, we have 200 equals 16t squared, and we can divide both sides by 16. And I know that 200 is at least divisible by 4. So that gives me that t squared is equal to 50 divided by 4. Now I can further reduce that a little bit, and I get t squared equal to 25 divided by 2. Now that I have 25 divided by 2, I can take the square root. Now I know something about t. T is time, and time can't be negative, so I'm going to ignore the negative root. I'm only going to take the positive one. So when I take the square root of both sides, I get plus or minus, but I ignore the negative one. Time is positive, or at least not negative. And that gives me 5 over the square root of 2. All right, so I have 5 over the square root of 2 seconds. It's falling with respect to seconds. So now we have the time when it hits the ground. So I'm looking at the closed interval then between 0 and 5 over the square root of 2. This is my closed interval. I need to look at my function and ask myself, is it continuous over that interval? The function is a polynomial function, so it's continuous everywhere, certainly on this interval. Is it differentiable there? Well, yes, again, it's polynomial. Polynomials are differentiable everywhere, so it's differentiable there. That is all that the mean value theorem requires. So there has to be a point C between open 0 and open 5 over the square root of 2 when it hits the ground, where the instantaneous velocity is equal to the average velocity. Now I want to find the average velocity, and I'll need to find the instantaneous as well. So what is my average velocity? My average velocity is going to come from the 2 endpoints. This is 0, 5 square root of 2, or actually, I've got it written backwards. Well, not written backwards. This is the time when it hits the ground, so this is time. But I'm looking at 2 ordered pairs. So now I need the time and the position in order to find the difference quotient. And remember, our difference quotient is y1 minus y2 over x1 minus x2, or f of b minus f of a over b minus a. Either one of these represents the slope of the secant line, which is our average velocity. Now, in order to do this, I need 2 ordered pairs. So what are my 2 ordered pairs? I'm going to look up here and I'm going to evaluate at the 2 different endpoints in time. So when t equals 0, I have that it is 200 feet up in the air. And then at time 5 over the square root of 2 seconds, I have that it's on the ground. So it's at 0 feet, right? So these are seconds and these are feet, right? So it fell pretty fast. In fact, I think that's a little too fast, but maybe not. I don't know. I've never tried dropping a ball out of a window of a high-rise apartment building. So we have two ordered pairs, and we can apply the difference quotient, which is the average velocity slope of the secant line. So we can do our 0 minus 200. So let's create some space here for us to work. So we can do slope of the secant line, which is equal to the velocity average, is equal to 0 feet minus 200 feet over, and then we have to use the same time from the same ordered pair, 5 over the square root of 2 seconds minus 0 seconds. And this is going to give me a negative 200 feet over 5 over the square root of 2 seconds. Now the units look good because it's feet per second. That sounds like velocity to me, but I've got a complex fraction. So remember that the denominator of the denominator basically flips up to the top, because to divide by a fraction, you multiply by the reciprocal. So this becomes, or works out to be, negative 200 feet times the square root of 2 divided by 5 seconds. Now, 200 and 5 are divisible by 5, so we can reduce this, and this tells me that the average velocity over that time interval is 40 square roots of 2 feet per second. All right, that's my average velocity. Now, if I've got the average velocity, what's the next thing I need to get? I need the instantaneous velocity. So at some point, these have to be equal. So I know that the average velocity and the instantaneous velocity are both going to be a negative 40 square roots of 2 feet per second at one point in time. I want to find that point in time. When are they equal? Well, I can set up my equation to say that the slope of the tangent line, which is equal to the instantaneous velocity, has to be equal to the average velocity, which is equal to the slope of the secant line. Now we've already got the slope of the secant line, the average velocity right here. What we need is the slope of the tangent line, the instantaneous velocity. To find that, we need to find the derivative. If we're going to find the derivative of our function, looking back at the original, we have negative 16t squared plus 200. When we take the derivative, you apply the power rule to bring the 2 to the front, and you get negative 32t. That first derivative represents the velocity. So remember that when we're doing slope of the tangent line, well, I think we called it s, so we should have s prime of t. That is the derivative, slope of the tangent line. So this tells us that negative 32t has to be equal to negative 40 square roots of 2 feet per second. And the negative 32, of course, is going to carry some kind of units in with it as well. So now I'm going to have units attached to it, which the units should have been, I'm trying to think what it was. It would be feet per second squared. So let me scoot this over a little bit so that we can see what it is. Feet per second squared. Remember that first term is coming from acceleration. So now what we have is we have negative 32 feet per second squared times time equal to negative 40 square root of 2 feet per second. The next thing we want to do is solve for that time. So when we solve for the time, we get the following. We get t equals negative 40 square roots of 2 feet per second, all divided by negative 32 feet per second squared. Now, what happens with the units? Remember that the denominator of the denominator lifts to the numerator. the denominator of the numerator and the numerator of the denominator go to the denominator. So basically the outsides are on top and the insides are in the denominator. It's the way it always goes for complex fractions. The 40 and the 32 are both divisible here by 8, and they're both negative, so we get a positive. 40 divided by 8 gives me 5, and 32 divided by 8 gives me 4. So I end up with the following: 5 square roots of 2 over 4 feet times seconds squared over feet times 1 second. The feet cancel, one of the seconds cancels, and I end up with seconds. And that is my final solution there, which is 5 square roots of 2 over 4 seconds. That's the time at which the instantaneous velocity and the average velocity are equal to each other. Let's take a look now at example 3. In example 3, we want to graph the following function and draw the secant line that connects the endpoints. And then by looking at the graph, we want to estimate the number of points C such that the slope of the tangent line is equal to the slope of the secant line. Our function is 3x cubed plus 2x plus 1 over the interval from -1 to 1. So I'm going to go back to Desmos and I'm going to graph this function, 3x cubed plus 2x plus 1. So this becomes 3x cubed plus 2x plus 1. And our interval runs from -1 to 1. So I'm going to change my interval here from -1 and the upper end of the interval to 1. So my closed interval is from -1 to 1. Now, I'm not got a great picture of it, so I'm going to move it around a little bit so I can see the whole thing. So it is a cubic, and it does look like I have the whole thing on here. So I want to connect this for the endpoints between -1 and 1, but I can't see the endpoints. They're not on there. So my graph is extending up pretty far. Looks like up here to 6 and down at the bottom down here to -4. Now you can leave the scale 1 to 1, but it makes it harder to draw. When you draw it, you can change the scale. It won't change the result. You will still be able to find where the slope of the tangent line is equal to the slope of the secant line. So I'm going to change my scale and make my scale for x go between -2 and about 2. And I'm going to change my y values to go between -5 up to about, let's say 7, so that I can get everything onto the graph, right? So now I can see the whole part of this function between -1 and 1. Now what I need to do is I need to draw a secant line. So what I'm going to do is I'm going to copy this off, if I can find my snipping tool, which it looks like I closed at some point today. Snipping tool. So I'm going to open up my snipping tool and I'm going to take a picture of this graph, which makes the room really dark. Sorry about that. All right, now I'm going to come over here and I'm going to paste my picture in. So this is what my picture looks like. Now take some kind of straight edge, credit card, student ID, index card, whatever you have, and connect the two endpoints with some kind of straight line. So it can be a little tricky to get it right on the end because of the width of the pen, but I'm going to do the best I can. There it goes, right? So it's connecting the two endpoints of the interval, and this becomes my secant line here in blue. Now I want to know where or how many points do I think where the slope of the tangent line has to be approximately equal to it. Take your pen and let your pen be the tangent line. Starting on the left side, hold your pen so that it's tangent to the graph, just touching at one point, and move it along until you think it's parallel to the blue line, right about there. So when I'm moving it along, I think there's definitely a point right around in here where the slope of the tangent line is parallel to the slope of the secant line. Then keep going. So once we're to here, it's parallel, then it flattens out. It's more flat than the secant line, even more flat, more flat. Whoa, it pretty much goes horizontal there. And then it becomes a little steeper, but not as steep as the secant line, steeper, 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 parallel. So I've got another spot up here, basically, where the slope of the tangent line has the same value as the slope of the secant line. So my guess is there are two places where I have that. And if we wanted to find these particular values, we could do that by finding the derivative, finding the average value, and then computing where those points are. In fact, for fun, let's do it. So let's go ahead and take a look at this one. We want to look at the average value first. So that is the slope of the secant line here pictured in blue. So we need to evaluate the function at the left endpoint -1 and at the right endpoint 1. So we're going to come over here and we're going to have f of -1 equals 3 times -1 cubed plus 2 times -1 plus 1. That would give me a -3 minus 2 plus 1. Is that what you're getting? I hope so. You're not here to tell me, so we'll assume it's right until I can prove to myself it's not. So I have -3 minus 2 is a -5, plus 1 will give me a -4. And then I can find the function value at the right endpoint, which is 1, which would be 3 times 1 cubed plus 2 times 1 plus 1, which gives me 6. Now I find the slope of the secant line by evaluating the difference quotient, f of b minus f of a over b minus a. So my value for f of b, the slope at the right endpoint, is going to be 6. And the value of the function at the left endpoint is going to be -4. And that corresponds to what I can see in my picture. Make sure that you use a double negative here because we have a minus for the formula and the value itself is also negative. That's a double negative. Don't make the mistake of having only one. Then we're going to divide by the difference in the x values. B is 1, minus for the formula, left endpoint is -1. This gives me 10 over 2 when you take into account the double negatives, which gives me a slope of 5. The slope of the secant line is 5. So the question is, when do I have the slope of the tangent line, the derivative, equal to 5? So I need to find a derivative. Well, I have the function right here, 3x cubed plus 2x plus 1. Let's take the derivative. So I get f prime, which is equal to 3 times 3 is 9x squared plus 2, and the derivative of 1 is 0. So I have 9x squared plus 2. Now this has to equal 5, that place where the slope of the tangent line equals slope of the secant line. So now I'm going to connect these two and set them equal to each other. So I have slope of the tangent line, the derivative, equal to slope of the secant line, the 5. And this gives me that 9x squared is equal to 3 when I subtract the 2 from both sides. Then I can divide both sides by 9, and 3 over 9 would give me x squared equal to 1/3. When I take the square root of both sides, this time I don't know that it's time, which means that I have to include the positive or the negative. This gives me two values, 1 over the square root of 3 and -1 over the square root of 3. These are the two places where the slope of the tangent line is equal to the slope of the secant line. Now we could find the y values for these by plugging those values into the function, but another handy way to do it on the graph is simply to graph a vertical line and see where it intersects the curve. Wherever it intersects the curve, that's the point we're talking about. So I can graph x equal -1 divided by the square root of 3. Did I get that in right? Looks like I did. And then I want the same function, but with a positive. So we'll take the negative off and it'll be positive, and we'll graph this one in black as well. So we're looking at these points right here where they intersect, which is at -0.577, -0.732, and at 0.577, 2.732. So we can tell that these are the mirror image points of each other across the origin, and so what are across the graph. So what we're looking at here are the 2 points where the slope of the tangent line is equal to the slope of the secant line. If we want the y value at that point, we would have to plug it into the original function, and we would come up with these y values that you see in the picture here. Let's now move on to the next example, which is number 4. In example 4, we again want to graph the function and draw the secant line that connects the endpoints and use the graph to estimate the number of points C where the slope of the tangent line, f prime of C, is equal to the slope of the secant line, the difference quotient. Our function this time is tangent of pi x divided by 4 over the interval from -1.5 to 1.5, which is the same as 3/2. So what we're going to do is we're going to come to our picture and we're going to graph it, tangent of pi x over 4. So let me remove what we had before and graph y equals the tangent of pi times x divided by 4. Close that. And remember that we're restricting our view to a closed interval from -3/2 or -1.5 to 1.5. X less than equal to x less than equal to 1.5. Close the restriction. Here is our restricted part of that tangent graph, which is right here. Now, if we want to resume a normal one-to-one correspondence, we can hit the house symbol on Desmos, and that will return us to a one-to-one graph. I'll make it a little bit larger so it's a little bit easier to draw the secant line and the tangent line, and we'll take a picture of it and post it into our notes. When we post this into our notes, and I'm going to make it a little bit larger over here as well, like this. And then I'm going to take my straight edge credit card, whatever you have. Mine's an index card. And I'm going to connect the two endpoints. So trying to connect the endpoints is always a little tricky. You have to hold it pretty still. Okay, so it looks like there. Notice that this is almost identical to the one we did a couple times ago. This isn't a whole lot different. What do I notice? Well, again, I think I've got 2 places. Hold your pen as a tangent line and move across until you find a place where it looks like the tangent line's parallel to the secant line. That's 1. That's 2. So it looks like we have 2, 1 here and 1 here. And we could use the techniques that we've used previously to find the exact values for those, but we're not going to do that on this particular problem. Let's take a look now at example 5. In example 5, we want to determine over what intervals, if any, the mean value theorem with its two conditions, continuous on a closed interval, differentiable on an open, applies to the function y equal 1 over x cubed. Now, the first thing we have to consider is to be continuous or differentiable, you have to be defined. So the first thing we should look at is the domain. The domain of this particular function does not include 0, since division by 0 is not allowed. So the domain is negative infinity up to 0, union 0 to infinity. So we know automatically that it won't be continuous or differentiable at 0 because it's not defined there. So any interval that includes 0 cannot satisfy the mean value theorem. Now what we're going to do is determine the conditions where it does meet the mean value theorem. When we look at 1 over x cubed, it is defined and continuous over the interval from negative infinity to 0, and again from 0 to infinity. However, it needs to be a closed interval. So we're going to let a be some value that is slightly smaller than 0. So let a be less than 0. Then we can apply the mean value theorem on the following intervals. And the mean value theorem is usually abbreviated MVT on the interval from negative infinity up to a, closed a. Now, you may say, but hang on, that left end looks open. Well, it turns out that negative infinity and positive infinity are considered to be both open and closed. So even though we use the open symbol of the round parentheses, that's because negative infinity is not a number, but it is considered to be a closed interval still. Now we have another interval, which is on the right side. And again, we can't include 0. So we let b be equal to some value greater than 0. And then we can apply the mean value theorem again on the interval from b to infinity. And that would be a closed interval as well, because infinity is considered both open and closed. Now let's take a look at example 6. Determine over what intervals, if any, the mean value theorem with its two conditions applies. Justify your answer. We have a natural log. Think about what natural log looks like. Comes up usually close to the x-axis as a vertical asymptote and then bends out like this. It's usually concave down over its whole side. In other words, it's bent downward, sort of like this. So what we need to remember is natural log will not accept 0 or any negative value. So that means that this 3x minus 5, the argument to natural log, has to be strictly greater than 0. So we take this and we solve for x, so we get 3x greater than 5, or x greater than 5/3, right? So we have this value right here. This is the domain. So this is our domain of the original function, which is from 5/3 to infinity. If it's not defined, it can't have the mean value theorem apply. It can't be continuous or differentiable. So now what we do is we look at this and we say, well, where would it be continuous? Well, natural log is continuous everywhere it's defined, and it's differentiable there as well. So that means that we can say that it would be, as long as we set some value greater than 5/3, let a be greater than 5/3, then the mean value theorem applies on the interval closed a to open infinity, or open closed infinity. It's both. Now let's look at example 7. In example 7, we want to show that there is no c on the open interval from -1 to 1 such that the slope of the secant line on the left is equal to the slope of the tangent line. We want to explain why the mean value theorem doesn't apply there. Well, let's take a look at our function and see what we think might be going on. The function is 1 over x squared. What's the domain of that? Well, the domain is all reals except 0. That's a problem because 0 is smack in the middle of that particular interval. So all reals, but not 0. Well, that's what our problem probably is going to be. It's not defined at 0. So how can it be continuous or differentiable there? It can't. So we're going to have an issue there because of that. It's not continuous over the entire interval from -1 to 1 closed, and not differentiable over the entire interval from -1 open to 1 open. And that means the mean value theorem doesn't apply. Let's take a look at what the graph looks like over the interval from -1 to 1 so that you can see more clearly what's happening in the graph. So again, our restriction for the interval is -1 to 1, and our function is 1 over x squared. You can see right away that we have a problem when x is equal to 0. I could change the scale and make it go from, let's say, well, where it is maybe, or even something in closer like -2 to 2 so that it's a little more spread out. And then let's make it go from -1, that's fine. Let's make it go up to, oh, I don't know, how about 300? Do you see that it never ever closes up? The graph doesn't close. You can't draw it without picking up the pencil. It's not continuous. If it's not continuous, it can't be differentiable. If it's differentiable, it has to be continuous, and it's not. So we have a point of non-differentiability and non-continuous. So right there at 0, and that's why the mean value theorem fails. Let's take a look now at number 8. Number 8 is a similar problem. Show that there is no C such that the slope of the secant line is equal to slope of the tangent line, and explain why the mean value theorem fails over the interval from -1 to 1. Again, we want to think about what could be causing a problem here. It's the absolute value. Think about what the absolute value of x looks like. Yeah, it's got this sharp corner on it. Now, it's not a problem having the absolute value under the square root because the absolute value will take any value and just return its magnitude. So it can't be negative, so we don't have that problem. And it's fine for it to be 0. The square root of 0 is 0. But the problem is the absolute value function has a corner on it. Now, if you're worried about the derivative and how does this work with the derivative, remember what the definition of the slope of, or rather what the definition of the absolute value of x is. So we can write f of x using the piecewise defined function, which would be as follows. If the value of x is greater than or equal to 0, then it's just x. And if the value of x is negative, we force it to be positive by multiplying by a -1. If x itself is negative, like -4, and you put a negative on the front, you have a -4, which is 4. So then this applies when x is strictly negative. Now, how would we do the derivative of that? If we want to do the derivative of it, remember what the derivative of a square root is, 1 over 2 the square root times the derivative of what's under the square root, chain rule. So this gives us 1 over 2 the square root of x, provided that x is greater than or equal to 0, since the derivative of x is 1. And on the second one, we do have to apply the chain rule because the derivative of -x is a -1. And this is when x is negative. Notice that those are not equal to each other. These are not the same thing. right? So we're not going to have a unified derivative formula. Now let's take a look at the graph and see if we can figure out what's happening. My guess is there's a corner in the graph, or a cusp, a corner or a cusp. So our graph is the square root of the absolute value. So we have square root of the absolute value of x. And I need to return to a regular graph, not being up at 300. So I hit that, and now I can scroll in a little bit, and you'll see that in fact, what we see is something that looks like the mirror image of a square root function on both sides of the y-axis and a cusp down here at 0. Again, that's where the two parts of the piecewise defined function connect, and they're not equal to each other, so we don't have the same derivative from the left as we have from the right. Therefore, the two-sided limit doesn't exist. Therefore, there's no derivative there. There's no derivative at the cusp. Now we want to take just a minute and talk about three important corollaries of the mean value theorem. A corollary is like a smaller theorem that is a result of the bigger theorem. So you prove the bigger theorem, and then you can state some smaller results as a consequence of it. Now, these corollaries actually become quite important in the work we do in graphing functions. So, for example, the first corollary that we have refers to if the value of the derivative is 0 for all the x values in a particular interval, then the function itself has to be a constant section. Okay, no, wait a minute. What are they saying again? What they're saying is you have an interval between A and B. And in that interval, the derivative is defined and it's always 0. Well, if it's 0, it's horizontal. Well, what's the only way that could happen? That could only happen if we had a horizontal section between A and B. So between A and B, the graph itself is a horizontal line segment. And then the derivative will always be 0 over that interval. That's corollary 1. What about corollary 2? Corollary 2 becomes very important when we talk about the fundamental theorem of calculus. What it basically says is if I have a function f and it's continuous over a closed interval and differentiable over the open, and if the derivative is greater than, oops, I'm looking at the wrong one. And no wonder I was like, that's not the one I need for the fundamental theorem of calculus. All right, constant difference theorem. If f and g are both differentiable over an interval I, and their derivatives are equal to each other over all the x values in the interval, so not the functions, but the derivatives are equal, then the functions themselves can only differ by a constant. That's it. So let's see what that means. So over here, let's suppose that we have something like f of x is equal to x cubed plus 2x squared minus 3x plus 4. And g of x is equal to x cubed plus 2x squared minus 3x minus 11. Now, if you're looking at those two particular values, you know that they are going to have the same derivative because they have the same variable terms. The only difference is in the constants. So when we take the derivative of the first one, f prime of x, we get 3x squared plus 4x minus 3. And when we take the derivative of g, we get the same thing, 3x squared plus 4x minus 3. Because the derivatives are equal, that means the original functions are only different by a constant. Why do we care about that? Well, basically, when the constant is different, all you've done is taken the same graph and shifted it up or shifted it down. This gives us a family of functions that all have the same derivative. So looking at it on the graph, we would have the following. Now I've got to remember what else I put. X cubed plus 2x squared minus 3x plus 4. All right. Now I need to scroll out so I can find it again. And there is my cubic function. You can see the majority of it, the important pertinent parts. And we'll be getting to how you know you have all the important parts in the next 2 videos. So we're looking at this one. We've got all the key points that we need. Let's put the second one on here, which is identical to the first, but it has a constant of -11 instead. So the constant is -11. What's happened? Well, it's the same graph. It's exactly the same graph. It's just been shifted down. So this gives us a family of functions which are all the same with the same derivative, but they differ by a constant. And we'll discover this is important in the fundamental theorem of calculus. Let's take a look at the last corollary, which is corollary 3, the one I started to do, which is applying to increasing and decreasing. We need a function that's continuous over a closed interval and differentiable over an open. Sounds like the mean value theorem. If the function is greater than 0 for all the x between a and b, then f is an increasing function. If the first derivative, the slope of the tangent line, is always positive, well, then it's got to be going up. The function can't go down, because if it goes down, the slope of the tangent line would be negative. So when the derivative is greater than 0, slope of the tangent line is uphill, then the function is an increasing function over that interval. When the function derivative is negative, then we know the original function is decreasing, going downhill over that interval. We're going to make extensive use of this third corollary in the next 2 videos when we discuss how to know whether or not you have all of those key points on a graph in your graph. We'll find exactly where the relative extrema are, where the x-intercepts are, vertical tangent lines, vertical asymptotes. We'll find holes, we'll find displaced points, we'll find jumps. We'll find where it's increasing, decreasing, concave up, concave down, where it changes concavity. We have to find all of those pertinent parts of the graph so that we can be sure when we go to Desmos that we pick a range for x and y that includes all the important parts. Let's take a brief look here at this picture, which will be the last thing that we'll do today. We have the derivative of the function greater than 0, which means the slope of the tangent line is positive. And you can see that the function is increasing, going uphill. Then between A and B, notice that the slope of the tangent line starts out horizontal, then tilts a little negative, then more negative, and it's decreasing. Then it reaches a maximum steepness called an inflection point. And then it starts coming back shallow again, but it's still sloped negatively until we get down to the bottom. So between point A and point B, the slope of the tangent line is negative. So the first derivative is negative and it's decreasing. Then again, from B out to however far it goes, the slope of the tangent line is positive, so it's increasing again. We're going to make extensive use of this in graphing functions in the next 2 videos. That's basically everything that I wanted to cover out of this section on the mean value theorem, and I hope you'll join me for another video on how to get the important parts of a graph on the graph.